Happy Thursday, everyone, and welcome to this Lightbend webinar for December 6th, 2018, titled Hands-On with Spark, Creating a Fast Data Pipeline with Structured Streaming and Spark Streaming. My name is Oliver White, Chief Storyteller and MC at Lightbend, and today we welcome Gerard Maas, who you can see via webcam at this very moment, to our excellent webinar program. Gerard is a published O'Reilly author, conference speaker, IoT aficionado, and a senior engineer on our fast data architecture team, where he focuses on the integration of stream processing technologies. While I introduce today's session and let others get settled in, I'd like to ask our audience a quick poll question. A lot of people are asking us about using Kubernetes with Spark. And so our question for today is, are you using Spark streaming or structured streaming on Kubernetes? That's obviously a typo. Now, if you're joining us today, then you're probably using or at least interested in Apache Spark for data analytics using fast data architectures that have really kind of emerged as the answer for a lot of us out there that need to process and analyze continuous streams of data. So when you combine Spark with other technologies like Akka Streams, Kafka and Mesos, Kubernetes, etc., this helps you really accelerate decision-making in your system and become reactive to the particular characteristics of your market at that moment. Now, Spark brings us various libraries like SQL-based analytics, fast data flow processing, graph analytics, and a rich library of built-in ML algorithms to address a wide range of requirements for large-scale data analytics. So in this toolkit, how do you know which part to use for the right job? And this is why Gerard is joining us today. We'll be taking a practical code-driven look at the two APIs available for stream data processing, the more mature Spark streaming module and its younger sibling, structured streaming. Now, for this session, we actually decided yesterday that it would be more helpful to our audience to focus on the live demo and code walkthrough rather than looking at the capabilities of Spark's APIs for streaming and their key differences. This is really something that you can find out for yourselves with just a little bit of searching. So instead, Gerard will focus on his code-based demo showing real-time anomaly detection, which, barring any technical issues, will feature live metrics as well as a camera feed for watching our IoT device in the real world. Gerard will show you the steps to take to get started with both Spark streaming and structured streaming, so you can feel more confident making the right choice for your next application and how to architect and develop streaming pipelines that you use either one or both of these APIs. Now, just a bit of housekeeping. As always, today's webinar is made possible only by people like you, encouraging your company to become one of Lightbend's hundreds of happy customers, such as our French client, CollisWeb, whose Scala, Akka, and Play-based platform has really redefined the parcel delivery process and helps make urgent logistics sustainable. They're looking for developers to join their team in beautiful Lille, France. You can find out about this on our website under the Customers are Hiring tab. Of course, today's webinar is being recorded and it will be shared with you next week. If you want to see the replay, if you have questions, add them to the GoToWebinar control panel, and we'll see if we have time to get around to them in the very short Q&A part of today's session. And if you are an existing Lightbend subscriber, then you probably know that you have unlimited access to our expert engineering teams, such as Gerard, through the customer portal, where you can ask additional technical questions, what-ifs, how-tos, and best practices. All right, that's all from me. Thanks for listening, and let's hand it over to Gerard Maas. Hey, Gerard, thanks for joining us.
Hi, Oliver. Thanks for the introduction. That was amazing. All right, let me get started here. Hello, everybody, and thank you for being here with us today. I'm going to take the webcam just a second, moving around. And this is sensor that Oliver mentioned earlier on, and we will be playing with that in a minute. If you are attending today, probably you are curious about what Apache Spark has to offer in terms of streaming capabilities. And even further so, you might be confused that there are two APIs out there. One of them being Spark Streaming that started about 2014 and has been deployed largely at many production sites. And Structured Streaming, who's been around for a year now, and really bundles the capabilities that has been built on top of the Spark SQL advancement of the last years. So what is one or the other offering for you? in order to create applications, and when do you want to use them? That's what we're going to do today. We're going to try to answer that question through a series of examples. I prepared a number of notebooks and codes that we're going to get through to show you how Spark streaming programming model, how it feels, what can we do with it, and the same thing with the structured streaming. Before that, I would like to introduce myself. Oliver already did that for me. Thank you, Oliver. I am a software engineer at the Fast Data Platform, and I focus particularly on that problem of making it easy for developers to get on streaming architectures, creating pipelines of different streaming technologies. That's a problem we are solving at Lightbend, and we hope that with the presentation of today, you get a bit more insight of what is that of a pipeline and how different streaming engines play a role in that. The agenda for today is nothing more than our title. We should be delivering on our promise, creating a fast data pipeline with structured streaming and Spark streaming. Let's first go through what is a pipeline? What do we refer with that? This is a brewery, and I live in Belgium, the country of beer. So if you remember anything from this presentation, let not be this, but please try them. Data pipeline is, in its core concept, the chaining of different sources and processors in a logical way, in a logical flow that takes source data from its raw form into a processed form that can be consumed by the upstream application. A typical architecture these days is that you have data sources around your enterprise. There are many sources out there. There are now connected devices everywhere. The new wave of the connected cars is coming at a fast pace. And as well as a lot of enablement and tracking of your users, what are they doing with your applications or with your games. All the industries today, they want to get insights of what is happening with the data that they have in their hands. And they want to do it as fast as possible. That's why it's not possible anymore to start writing the data to a large database or to a large Hadoop cluster, and then only applying some transformation logic at the end of the day or at the end of the week. Those days were gone. Today, in today's industry needs, we need to take that data and extract as much value as soon as possible. The data value decays with time. So we want to have that value from the data from very fresh data. One way to do that is having this data pipelines concept in place that allows you to create streaming applications through thinking about them about composable elements in the same way that we are thinking about functional programming being functions that you can compose by applying one over the other to some data element. Streaming pipelines come from that very definition of there is a source, there is something that processes the data, came from the source, and it produces the data somewhere else. If that somewhere else is again another streaming component, then you can chain them together. And the key elements to keep in track here in place is that contract, that data shape in between them needs to be well defined, needs to be in particular schema driven if you want a suggestion. The second thing that data pipelines are enabling for us is using the best tool for the job. There are a plethora of streaming engines out there. On Spark, we have two, as we mentioned just at the beginning, but we also have Kafka Streams, we have Flink, we have Akka Streams, and every time comes the question, what is the best tool for the job? So they're very different, and it's very important to understand each one of them to know their pros and cons and how they play with the application that you have in mind at a given point in time. for that, using a pipeline that might be initially consuming the data using Akka Streams, cleaning that data, enriching it, and then producing it to Spark for a distributed cluster processing, maybe some machine learning that needs to be applied to that, would be a very appropriate application for that. You don't need to use exactly the same hammer for every data needle or every data nail that is out there. The third element, and this is very important, is a network effect of creating pipelines. Why? Because once we have deployed that component that takes some data in and produces data at some other site, then we can reuse that data. And we can, especially making use of that consumer producer model and the subscription subscription model, that you can connect to an existing data source and start consuming that data. So existing and deployed data sets become also data sources for new applications. That makes the possibilities of your enterprise, of growing your application base, is infinitely growing in a network effect. So that we have already a concept of what a pipeline is. Let's see the tools of the job of today. We are dealing today with the structured streaming and Spark streaming, that we mentioned that, and I guess you wouldn't be here if we were not talking about it. What are those two APIs? So right at the beginning of times, we had Apache Spark. We had the core that was dealing with data at rest. It came with an abstraction called RDD, the Resilient Distributed Data Set, and that allowed to distribute functions, apply computations to data when the data is distributed in a cluster. Shortly after the first version of Apache Spark, the 0.7, I think one of the first versions that was out there in the open source, Spark streaming came out and defined a new abstraction. The D-stream, or discretized stream, creates a view of data over time that can be translated into those RDDs. It's understood today in the industry as a micro batch model. Why? Because data that is coming into your system is chopped into segments taken over time, over a regular time interval, and every one of those segments becomes an RDD that can be processed by Apache Spark. Then at the left side of our spectrum here of different libraries built on top of Spark, we have the structured streaming. Structured streaming builds on the abstractions created and introduced by Spark SQL. We have the Catalyst engine that is able to optimize queries over different data sources, and we have that data set abstraction in data frames. Data frames was inspired by the Python pandas and the way of dealing with data from a tabular perspective, thinking about the data as being on a table. Structured streaming takes that concept one step further and says that the stream is a table, and we can think about the stream in terms of fields and records that are coming on a table one by one, and that's a very logical or very simple concept to understand. You have, for example, when you have a database and you insert data, that data is coming as a stream. You never have a 1 terabyte database from day one. That data came in record by record. And structured streaming uses what is called that table stream duality to give you a programming model and a mental model to think about streaming just as queries that you can apply to data as if it were on a table. And using that mental model, then you can really apply that to a streaming data as well as a batch data. You can reuse that knowledge across the Spark SQL data frames for batch and for stream processing. All right, how do they look like? Here they are side by side. We have a structured streaming on the left and Spark streaming on the right. Spark streaming is very much functional programming oriented. We will recognize there a lot of these functions of collections in Scala. Initially was inspired by that collection API in Scala. So we will find these flat map functions and these reduce functions with some closures that are containing as well a function. So there are high order functions. On the left, we have a structure streaming. Structure streaming mixes that feeling of functional with then a more declarative approach. There we are saying that Spark, please read this stream from this location. And once you have this stream, please apply a given function. In this case, is flat map. But you see here that we are not dealing with the low level adding a one to a word and then applying a addition function that in a reduce by key. We are saying in a very declarative way, in a very SQL-like way, words, please group by a given value and count that result. And that line is actually summarizes the whole operation of this ubiquitous word count application. Like this is like the hello world of the big data world. But it's important for us here to realize that subtle difference in the way that we create the API and we create our applications. I'm going to give you this. This is like a too long, didn't read summary of the difference between Spark streaming and structured streaming in terms of time, execution, and abstraction. And as you can see there, there are key differences. In terms of time, structured streaming provides us with a abstract view of time. You can use the processing time, meaning the time when the data arrives to your processing system, to your data center, to your computer, to your processor, or you can use event time. And event time is the timestamp that was applied to the data at the moment it was produced. When your, let's say, when your watch recorded your heartbeat intervals, when your car reported a given failure, when the traffic lights were sending some signals about traffic loads on the roads. Those are timestamp events that are being sent from the source with the time already. And then structured streaming gives you some abstractions to deal with that directly without having to really encode it in your own logic. On the other hand, the Spark streaming uses this microbatch, this initial model of microbatching, and is fixed to a given interval. That interval needs to be defined beforehand and determines all the operations that you can do in Spark streaming. For example, if you start with the interval of 30 seconds, so every 30 seconds you want to process new data, and you want to apply a window, so that window needs to be a multiple of 30 seconds. Might be 1 minute, might be 2 minutes, but you cannot have a window of 45 seconds, for example, because you need to be bound of that initial decision of that streaming interval. This has consequences, and it was one of the reasons because of the evolution towards structured streaming and to make that abstraction of time, making possible to introduce event time processing as well. At the execution level, we have on structured streaming, we have 3 different modes. One is a fixed microbatch. Internally, you don't see it, but it's the way the engine is working. And it can be also tied to a given interval of time. This is very interesting in some industries where data is arriving in regular intervals and you want to really clock that also in your internal processing of the application. Then you have a best effort execution. It's also microbatch, but every time that microbatch is done, it will take the next one without waiting. And it feels like near real-time behavior, because when you have capacity in your cluster, then structured streaming will be crunching over the data as fast as possible. It's best effort, and will deliver actually the maximal capacity of your of the cluster that you are using. And then there is this new experimental model called continuous mode that is answering that question of, I want to process data in near real time. I don't want that micro interval. I don't want latencies of over a second. I want latencies of under a second in the order of the 10 milliseconds. And the continuous execution model gives you that. with some restrictions today. So it's currently in experimental mode, and it has a number of restrictions. There are many applications and many parts of the API that are not usable if you want to execute your application in continuous mode. But it's an advance, and I believe that the Spark will be moving in that direction the years to come. On the side of Spark streaming, we mentioned that time interval at the beginning, and it reflects also in the execution model. It's tied to that microbatch, so every that interval of time, we will be gathering data, processing it, and passing it through our logic. At the end, we have the abstraction. What do we work with as developers? What do we need to develop? What do we need to create in terms of code? In structured streaming, is based on the data sets and data frames abstraction. So we will be using SQL functions. We will be using very high-level logic that help us to develop applications much faster, but sometimes we will also show some limitations when you need to do very specific coding. On the other hand, we have a Spark streaming with the RDD and the dstream abstractions, and there you can go. It's a lower level API. You have more access to the functions of the cluster, like the scheduler, as I mentioned there on the start. But then again, you also need to invest more time and more cognitive investment into understanding how is this working and what things are running in the cluster, where things are running locally, and to realize and to achieve the use case that you want to implement. All right, and with that introduction on pipelines and the two APIs we are going to deal with today, let's get on with our application. I mentioned pipelines, and I want to show you an example of that. And in my example, the things I'm going to bring you today, I would like to do some anomaly detection. It's a simplified example. It is for us to experiment with the API to understand how it's working. So please don't use it on your nuclear plant. But what we're going to show, what I'm going to show you here is how to really get it going with every one of those APIs, and how can you create your own pipeline for your own purposes. Here we have a sensor. That sensor is here right next to me. This sensor is a sound sensor and captures the levels of sound in the environment. And we will like to see when we have a certain anomaly, when we have a loud sound or noise in our environment that is not the usual. So, for example, if we're here and uploading, then we will see that we'll have different levels of noise, and that sensor will be capturing it. We are capturing that using an Akka-based microservice, and that microservice, we call it a data multiplexer because it creates 1,000 other sensors, replaying some data that was previously recorded. And that is, it wouldn't be kind of distributed data processing if we were used processing data from one sensor. So I would like to give you a feeling of what is it to have a more substantial stream to process. So we will have like 1,000 sensors producing data into our pipeline. First thing we're going to do is to do some exploration of the data, see how the data looks like. Then we are going to prepare the data based on our initial exploration. There might be areas we need to address. We'll address those areas in the data preparation that becomes the entry point for our pipeline. The first part, once that data preparation is done, we will then produce the data again into our transport and Kafka, and it will be picked up by our second part of the pipeline. Is an online model for determining when one of those sensors is presenting an anomaly. We will be doing this using Spark streaming. And finally, we are going to consume that product that is created here, that the parameters of that model, and we're going to join it with the initial raw stream to apply this anomaly detection. Depending on how we do in terms of time, can go into details here, but all the resources are available online. I will give them to you at the end of the presentation. All those notebooks are in GitHub. So if there is something that we need to cover likely today, you can always go back to those notebooks and ask me questions later on. Okay. In terms of how this is done, we are going to see that each one of those notebooks is getting data from Kafka, so the architecture of the system, we call it like that. We have that sensor connected through a cable, because I use this in conferences. I cannot trust wireless communications. And we have the sensor multiplexer. Is a process written in Akka. It's a microservice that will be producing that data onto a topic in Kafka, and that topic in Kafka then will be consumed by each one of the processes that are comprising the pipeline, and then returning data to Kafka when that's required, when it's not the end point of that pipeline. For example, if you are driving an application or driving a dashboard, then the dashboard probably will be the last element on a given pipeline. There will be not more transformations after that. This is a sensor inside. So the sensor is made of a processor. This is a processor with a Wi-Fi chip. And there is a sound sensor connected to that, and a LED array. And the LED array gives immediately the values that the sound sensor is detecting. Next to that, the data is reported through USB, and it can also be reported through Wi-Fi to any receiver. Okay, so we are done with introductions, and I hope you're looking forward to have some real coding here, because that's what we are going to start doing right now. The weapon of choice of today is a Spark notebook. And the Spark notebook is a notebook implementation. There are several out there, like we have Jupyter, very popular among data scientists. And we also have Sibling that implements several backends, and it's very rich in the number of libraries it supports. I like to use the Spark notebook today because it has an exceptional support for streaming applications. All the widgets in the Spark notebook are reactive, and you can give them data back from the context of the notebook itself. So we don't need to be doing this, some of the dirty tricks that are used out there, kind of refreshing completely a chart to do some updates. We can do it from within the notebook itself, and we will see the results immediately. The first thing we are going to do is explore our data. And for that, we have this exploring sensor data notebook. First thing we're going to do here is to have some common definitions. This notebook takes the data from that row, it's called sensor row topic. And it's consuming it, and we will do a visualization with it to gain insights, to gain intuition of how the data looks like and what our next steps should be. So first, those are common definitions. They are necessary, but not really important for our discussions. Here is the first element I would like to highlight. How do we read data from Kafka using structured streaming? It's very declarative. So we say we read the stream and the format is Kafka. When we say the format is Kafka, then behind the scenes, there is a Kafka source that is going to be created, and we're going to pass these configuration parameters to the Kafka source and load the data. So we load the definition. We don't actually load any data at this point in time. We're just saying, declaring our intention to have that data source. And that data source is a streaming data source, and we can see the schema. Structure streaming, the word structure refers to the structure of the data, and that structure is represented in terms of a schema. We need a schema information to work with structure streaming because it uses that schema information to go into a field level representation of the data, and then do some very interesting things with it, like direct binary addressing or code generation. So when we understand how the data looks like, we can do certain very interesting stuff with it. For that, we need to provide a schema. And the Kafka source provides a fixed schema. It's this key value topic partition. So we have the key and the value and some metadata in that envelope. That's not what we want. We want that the actual data that is flying through the system, the data that we gave Kafka, that sensor data that we are producing with our sensor. And that is located in that value field. To do that, we're going to parse the value that is contained there. And in order to achieve that, we first need to declare how that data looks like. So we have a sensor data. We are here creating a case class in Scala. And Spark has the facilities to extract a schema from that case class instead of writing the schema by hand, which is what happens very often out there. And I find that a case class-based declaration much easier to work with. Otherwise, we will be writing this stuff. Once we have the schema in place, we can use that schema to apply a parsing function. And we are going to do this using this from JSON function from Spark SQL. So that field called value that is in our original raw data stream. First, we're going to transform that into a string because it comes in as a byte array. We transform that into a string, and that string is just encoded in JSON. And we are going to parse the data contained by the string using a JSON parser, providing the schema that we just declared up there. All right, now we have this, and we have finally a sensor data stream that is a data set. So this is a streaming data set, very important. Now we are dealing with a string declaration that is strongly typed, and it has also a schema internally. So we can see here it has an ID, a timestamp, and a value, which is, of course, the same shape as the case class that we defined earlier. Let's visualize this. For the visualization, I'm going to use the first of the, let's say, a very easy to use sink for structured streaming called the memory sink. And that memory sink creates a local SQL table, a temporary table in the Spark memory that we can then address using SQL operations. All right. So what's happening here is that data is coming in through the stream, and directly we are immediately writing it to this in-memory table so that we can query it. And here we have our first SQL expression. We want to select everything from that table called visualization that we declared up there. Once we have that, we can observe the data that is flowing through the system. So we have a number of sensors that are simulated and their values and the timestamp. So that's all looking really good. We can also see how much data or how many records we have received so far. And an interesting property is, of course, that we have a streaming source. So every time that we count here, that we count this target table, we see that we have more and more records. And that will not stop because our stream system is working 24/7. The last thing we're going to do is to visualize the data. We want to see how that looks like. And to do that, I'm going to use one of the built-in chart widgets in the notebook. This is a line widget. And to keep updating it all the time, we are going to use some low-level threads programming here where I'm recurrently executing a query to get data from that chart. And now that we have the chart, we are going to visualize the chart here, and we should see some data there. Perfect. Okay, so we have our first very simple application. There is a source from Kafka. There is a sink. It's in memory. We are querying that memory table, and we can observe how the data behaves. We see that the data contains a lot of noise. Of course, it's recording now the noise levels in the environment. I have put my webcam here out to show what happens when we have some really loud events. So we see there that the sensor is recording high levels of noise in the environment at that point in time. And this is the kind of thing that we want to detect later on. Okay, so two observations here. Our baseline is very far from peaks that we can capture from the sensor, but also our baseline is really jagged. It contains a lot of noise. Of course, it's picking up the noise from the environment. But we would like to work on that a bit. We would like to clean up that signal so we can have a smoother signal as input for our anomaly detection system. I'm going to stop this, and I am going to then move directly to our next notebook. What we just did was to visualize and get insights in the data, and then decide what we are going to do next. This is a very classical data science approach. The first thing you want to do is to gain intuition of the data. I'm going to shut down this notebook. We don't need them anymore. We don't need it anymore. And we are going to go to number 2. We are going to improve the data quality. We would like to get rid of the noise present in that feed and create a baseline, and then that will allow us to observe peaks easier. Okay, the same thing as before. We just need the definitions. We just need the location where Kafka is located. We need the name of our topics we are connecting to. In this case, we are also removing a checkpoint that we are going to use during this notebook. And if we don't remove it, sometimes bad things happen because it cannot recover from the previous state, but I don't want to do that today. You do need to recover from previous state when you are going into production, of course. I am not recommending you to do this in production, but it's okay for our purposes. So first thing we're going to do is read the stream. We already learned how to do this. Again, we are reading from Kafka. We have a schema definitions. We are parsing the payload using JSON. We already learned, and I'm trusting that you all have this in your heads already, so we can just jump over it. Okay, and the interesting part starts here. We're going to introduce here the concept of event time and how it is implemented by structured streaming, and how can you use it. The first thing that we do with event time is say where that event time is. So we define event time as being a timestamp that is provided by the source of that data, and not as opposed as when the data enters your processing system. So it is the sensor, or is the processor, or is the computer that generated that data that's put in the timestamp. And there is a record flying over the network, and we capture that record here. We need to tell Spark, this is what we understand from this data that is a timestamp. Maybe we have just a bunch of longs in one record, so we need to be specific. How do we do this? First, we need to give it a specific schema. There are 2 ways of doing this, and one of them is transforming that long into a SQL timestamp. Then the Spark will understand it immediately as a timestamp, but we also need to say, okay, that timestamp column that we just declared there from our long input. So we have our input data, this being a long. And I'm going to use it as a watermark. The concept of watermark is, this is as the length of time I'm going to wait for data that is out of order or data that is being late. If I am producing here, in this case, I'm going to produce a window. Every 10 seconds, I'm going to produce a window of the last 30 seconds of data. But there might be data that didn't come in the right order. And how do I know? Well, we actually don't. We need to wait for the data. And watermark is the way of saying to the system, I will allocate 10 seconds of my processing to wait for any data that might be late. And of course, we have a closed system today, and in this system there is no out of order. But and out there, we always observe that this is the case. You will have some laggers, connection problems, systems that run out of battery, and when they are reconnected, they report back the data that they recorded last week. So is that data valuable or not? That's the question that we need to answer here when we set that value. For me, anything that is beyond 10 seconds is too late, and we can move on. The next thing I'm going to do is to do a group by. This group by function comes from Spark SQL. Again, we are seeing that the surfacing of all those SQL facilities that are also available to be used in structured streaming. And one of those is use the aggregation function, and I'm going to aggregate the value over the average value of that value, and I'm going to call it average value. And let's move on with it. It creates a different schema from before, so that the window will have a start and an end. It will have a timestamp on each one of them, and we have access to that average value. What do we do with this? Well, I introduced at the beginning the concept of a pipeline. I might be interested in reusing that data several times, not only once. So I am going to write it back to Kafka, and then I will have a topic that is the source of average out or clean up data in my system that I can then later on consume for further investigation or for further application creation. All right. So to that purpose, I have converted my window information into a JSON structure. And this JSON structure is then embedded into a value field. The Kafka writer, so the Kafka sink that we are using here, require us to have a very specific shape for that data. In the same way that it produces a very fixed schema, it also consumes a fixed schema. And that fixed schema is having a key and a value. And then our key is the ID, and our value is a composition of these three elements. Once we have that in place, we can write our data to, it seems it was already created, and let me just update this. Oh, why is that? Oh.
It's the demo gods, Gerard.
Yeah, it's a demo gods. I forgot to give my offers before starting. All right, but that's solved. And now we would like to see, and especially in this case, I would like to be sure that we see progress here. All right, we are writing, so we are consuming data and then producing data. If we update this again, we should be seeing different results. There we are. Okay. Okay, so what's happening here is that every 10 seconds, I will be providing 30 seconds of worth of data to my downstream topic. But the first batch will wait for a full 40 seconds. Those are the 30 seconds of the window plus the 10 seconds of the watermark. That gives us a bit of time to move to our next notebook. This next notebook we have here, I am going to just execute it really quick. What we're going to do here is what we did at the beginning, just visualize how that data looks like. And what we are expecting is that that data looks pretty different from the original data that we saw at the first notebook. Okay, so there we are. The data is smoothed out, so we don't have those high peaks and the recurrent peaks and those jagged peaks in the data. We have an average of 30 seconds, and every 10 seconds we are reporting that moving average. So here you see the timeline in terms of seconds since the start of the hour, and every 10 seconds we have a new value, but that value is really smooth. It doesn't contain that amount of noise that we were seeing before. And that's actually what we wanted to see. So we have now the original source of the data and a second topic that is that cleanup data, that noiseless data that we can now consume to create our model. And let's get on with that. Okay, so first thing here is we are going to shut down the visualization, but not the structured streaming application. Why is that? Because this is now part of our pipeline. It's running the code that we are, where we implemented the cleanup, and that is required by the downstream applications to further function. Next up is the third notebook. This one might be a bit dense, so I'm going to focus very specifically on one single element that I like you to capture from this notebook, and that is how are we implementing our own computation using the API, the low-level API of Spark. This is I have had clients where this became a critical part. There are sometimes very complex requirements in our applications, and although those high-level SQL functions are really easy to use, and you can go working with it very fast, and sometimes you hit limits. One of them is trying to distribute work on a cluster, and that's what I want to show you in this example. We're going to create a standard deviation model, and to do that, let's say the math that we saw on our high school, illustrated here by this function. So our teacher told us that we need to have all the data, and then we need to calculate the mean of the data, and then we need to start doing the difference of every element. So the square root of the difference of every element, sum that up, and then divide it by the number of elements minus 1, then we do the square root of the whole thing. That is, let's say, the classical high school definition of the standard deviation. But what happens when we don't have access to all that data? Then things start getting a bit interesting. We cannot just compute this function because we don't have the end elements in our hands. We have only one by one, and we are having that data streamed to us. We cannot wait till the day or anything to do this computation. We want to do it online. Luckily, there are very smart people out there that have solved this problem before us. And there is an implementation documented here in this Wikipedia article. It's called the Welford's online algorithm that defines a way of how we can compute or actually approximate the standard deviation and the mean of a set of observations when those observations are coming in a streaming fashion. And I would like to implement that for you today. So the first thing we're doing is defining this case class that is going to hold our state. This is having the number of elements, the mean, and that M2, that's the sum of the mean squares over time, and for each of the elements that we are observing in the data stream. And the second thing is that we are holding a map of them in local memory. Why is that? So we are getting a lot of streaming data, but the number of devices that we have is limited. So the data they produce is unlimited, but the cardinality of those devices is limited. So we can hold that pretty well in memory. That's no problem with that. What we need to do is scale up the computation and then bring that computation back to our local state. This is what we're doing here. And I will suggest that you go over line by line on the GitHub repository. But let's say in the course lines, what we are doing is that we are taking that D stream that is coming in. The D stream, as we mentioned, is an abstraction that is saying I have an RDD over time. So that RDD is a set of data that is distributed in a cluster. And I'm going to map that data set into that computation that I need to do. And was as part of the algorithm to determine the three parameters of my model. I mean, the number of elements that I saw for that ID, the mean of that ID so far, and the sum of the squares of sum of the means of the squares for that ID. Once I have computed that in the cluster, I'm going to bring that locally, and I'm going to store that into the map I declared before. So this is sometimes mind-blowing in the sense that we have really a large data set coming in. We are delegating the computation to a cluster, but what we are interested at the end is only in the results. And next to that, we have two functions, one for predicting and one for training. Now, this is getting a bit slow. Okay, so I'm going to execute that. And now I'm going to create a streaming context. I'm going to create a stream in Spark Streaming, the same way we did in structured streaming, but using the Spark Streaming API. In the Spark Streaming, we use a different context. So we are not using the Spark session that is common to the Spark SQL implementation, but we need this separate streaming context that needs this Spark context that is contained in the Spark session. I hope you got that. All right, it's a little bit like Russian dolls. The Spark context is required to create that streaming context once we have this, and actually you just need to learn it once and you can do it every time. And then we are going to declare a stream, a direct stream from Kafka. This is very different from the, let's say, the very nice read stream declaration from a structured streaming. It's a little bit more like low-level coding, and gives some warnings there that we can safely ignore. And we also need a schema for our data. There we are not going to escape from that. And that's something that I always recommend in streaming applications, is to always adopt this schema-driven approach. The schema becomes the contract between the different components that are participating in a streaming application. Now I'm going to do some local bookkeeping. I create this model that is local to the system, and I'm going to transform the data. In this case, I'm calling from Spark Streaming into Spark SQL. So those are functions available in Spark SQL, very similar to that SQL function we use in structured streaming, where structured streaming is embedded in Spark SQL. Here, instead, we call out using the Spark session, we create a data set. So we actually calling out into that API to create the parsing function that we require. Very handy to know. You can use from Spark Streaming, you can use all the other APIs available on Spark, and many available APIs out there as well. It's very programming friendly in that sense. All right, so here we are doing declarations. We declare that data stream, and we transform the data stream into the sensor data using the schema that we know. And we are going to pass that data to the model. So we're going to train the model using the data. And once we do it, that the step of training, then we are going to score that same the same stream with the model that we are estimated. So of course, here the model is incremental, but the training it's happening on the last batch of data that is coming in. And we would like to see that this thing is doing something for us. So I am going to declare some widgets to observe the data. Here we have a scatter chart, sorry, that is giving us the difference between the values and the standard deviations. We can observe the behavior of the data there. And nothing happens. So now I'm just declaring elements in my in the context of my process, where I have this stream output that we are going to populate once the stream works, once the stream starts working, sorry. So everything comes down to really giving instructions in that context that we initially created. And at the end, we're going to say start and start everything. And at that point in time, then the whole process will be translated into a Spark job, and Spark will be doing its work on the data as it comes in. Okay, the last thing we're going to do here is to write that data back to Kafka. And the data I'm writing is the model. So I'm not writing the sensor data anymore. I'm writing the models we created, that standard deviation estimation that we have, so that we can do some anomaly detection later on. Okay, so we have there start streaming context. All right. And as I mentioned, we have that concept of a streaming interval, this batch interval, and we need to respect it. So there will be something like 30 seconds before anything happens here. And once that happens, and we start seeing data coming in. The data is coming in. This is just sample data that we are receiving from our previous notebook that is creating that cleanup feed for us. And we have a output box for detected anomalies. There are no detected anomalies here. Sometimes it takes a little bit of time to pick up because at the beginning, that model needs some time to train. We can try to see if we can detect or sense or provide an anomaly in this case, but we will see that sometimes it takes a little while, and I don't think we have the time to wait for it. Okay, but every 30 seconds we will have a result being played out there. The more important thing is that we are producing now the results of the estimations of our standard deviation downstream, and we can go on and use that in streaming detection notebook. I think we will kind of wrap it up at this notebook and leave it as homework for you guys and girls to observe at home. And what it's doing is something very interesting. It's combining Spark streaming and structure streaming together to obtain what we call a control stream. So a Spark streaming, and let me go right down to the interesting part. And this one is here. Okay, so we have a combination of a Spark streaming that is reading that model that we just received from upstream, from that model we created in Spark streaming. We receive it here, and we are going to materialize the data from that model and use it into structured streaming to do some near real-time estimations of when a sensor is going is presenting some anomaly, when we see some anomalous behavior there. And the combination of the two is very powerful because Spark streaming takes care of the bookkeeping. It takes care of handling those models coming in. We are using this same pattern to do machine learning model serving. And the surrounding stream is feeding the model parameters into this inner stream that is doing the scoring. So we can see that this being a slow stream that is updated every 30 seconds, like we saw in the previous notebook. And this one is going as fast as possible. So it's going near real time and producing those results back to Kafka. All right. Please check it out. There is also a visualization built for that one, and it will show you how the data in forms of bubbles, how the data bubbles up when an anomaly appears. Let's go back to our presentation right now. So now we have gone through a whole gamma of different patterns and applications for the two APIs that we are interested in today. And let's try to bring then the highlights or the very specific points that I would like you to take home. We had this first notebook where we did data exploration. And as you might have noticed, I used that data science approach. We go from data exploration to data cleaning and preparation. Then we produce the model, and we finally apply the model to create a result or to obtain value from the data. In terms of what we learned today, the exploration part has presented the use of the Kafka source, the memory sink, and some SQL operations. On our data preparation notebook, we saw how we can use event time from the data itself. So we declared a field in that record coming in, saying this is the event, and we applied watermark, a window to it to obtain a moving average that we will route then back to Kafka using the Kafka sink. Next, we used RDD low-level programming to implement an algorithm that we found on Wikipedia, and that was pretty low level on its own, to do the online computation or estimation of the mean and standard deviation of a data set. And we used that to try to estimate when a sensor is showing an anomaly. We also saw we are computing in the local and distributed environment. So we use the RDD transformations to apply the algorithm distributedly, and then we broke that data locally. We also use the they saw the use of Spark SQL, where we called out to the Spark SQL functions to parse the data that came in as JSON and transform it into our case class-based data data format. Finally, we use the Spark streaming Kafka source and sink to interact with Kafka and the data going through that. The last notebook where I glanced over, I focused on the very important aspect that is illustrated there and you can see at home, is that we are using a control stream pattern where Spark streaming is providing, let's call it the slow batch-based update of machine learning parameters to a fast-running structured stream processor that is scoring the data as fast as possible with the latest and greatest set of parameters that came from the previous notebook in that pipeline. All right, so at the beginning I showed this matrix where we touched into the different characteristics and let's say highlights of the two APIs. I hope now it becomes very clear how the time abstraction in structured streaming works. We use that event time, whereas in the Spark streaming we had a fixed 30-second window where we had to work in. We saw the execution or initial chart was updating as fast as possible. We saw the driven by the sensor data immediately updating and showing the peaks when I was doing some loud noises, whereas we had hard time trying to find back or anomaly in the fixed microbatch model because we would have to wait 30 seconds, or if we miss the first 30 seconds, the next one will be in the next minute after that second round of 30 seconds. So it gives us a bit more delay in when we see the data. The abstraction, we saw how easy it is to create sources from Kafka. There are many others. There's network sources, file sources supported, and many more coming. And on the Spark streaming, we saw the power of low-level programming using these streams on RDDs. All right, and with that, I am concluding the presentation and this hands-on session on working with Apache Spark using the streaming APIs like Spark streaming and structured streaming. This is our fast data platform where those APIs are supported together with Akka Streams, Kafka Streams, and Flink. And of course, we have our gamma of microservice technologies where you can implement your microservices and combine them with the fast data applications to deliver value to your company, to your customers. Some resources, the notebooks I used today, you can find them all there. If you have any questions, please, you will see my contact in the next slide. There is a presentation about pipelines and the ideas that we are having about pipelines and something we're working on. I cannot disclose too much, but if you go to that Reactive Summit presentation, you might see a little demo there that was very interesting. On the Reactive Summit, also, I talk more about how Spark streaming and structured streaming works. If you are more interested in having additional background on the model, you might be interested in that presentation. And there is our link to the Fast Data Platform if you would like to learn more. And there I leave you with my contact coordinates, and my book will probably be out there early next year if I don't sleep until the end of this year, which sounds like the plan. And with that, I would like to thank you. And if you have any questions, please use the chat to provide the questions to us. And thank you very much for being here with us today.
All right. Thank you so much, Gerard. I think the feedback from the audience was very positive. I think this was a really excellent demo. And I think the real value for a lot of you out there will be to be able to replay Gerard's demo and have access to the notebooks and links that he shared. Unfortunately, we've gone a little bit over time today, so we're going to omit the Q&A. However, Gerard is a very active Twitter person, so you can reach out to him at MaasG, as you saw on the slides. And we'll be sharing this video recording and the slides with you next week. So thank you very much, Gerard. Thank you, everybody. for tuning in today, and speak to you next time. Bye-bye.